All right, thank you for the introduction. Then today I'm going to present our paper called TrioSim, a lightweight simulator for large-scale DNN workloads on multi-GPU systems. Well, I'm the presenter today, but the true hero behind the scene is our first author, Ying, who is a PhD candidate at William Mary. And she will be on the job market by the end of the year. So if you want to bring this critical infrastructure to your institution, that prepares yourself for the next generation LLM infrastructure, LLM computing, then you should give her an interview, okay? So as you can see, there are many authors in this work and there are many affiliations in this work. So the context of this work is under the affiliation, under the collaboration between Light Matter and William Mary. So Light Matter is a company that provides photonic-based computation and communication technology. Especially we care about this technology called Passage. So Passage is a technology that provides photonic communication for wafer scale GPUs. Then they have ultra high bandwidth, low latency connection for these GPUs on a wafer. Then our target is for large scale machine learning training workload and to solve the scalability problem. So considering how to design this type of problem, we do not have a good tool to use at the beginning. So we develop our own tool that becomes TrioSim eventually. So we all know that we're in an era of LLM, that workload is getting larger and larger. Like it's reported that GPT-4 is using 25,000 A100 GPUs, spend almost several months to train this type of workload. And also at the same time, vendors are building devices larger and larger, like NVL 72 GPUs, integrate 72 GPUs in one platform, right? So we're basically in an era that's defined by large compute, large memory, and large communication. And we're all researchers, and we want to do research in this type of domain, and we need tools. So what tools we like the best? We like simulators, like all the presenters in this session. We use simulators, but our simulators for GPUs, other than the GPU simulators presented in this session, we're mainly focusing on XOSIM, multi-2SIM, or MGPU sim. These simulators are instruction level, cycle level simulations, so they are 1 million to 100 million times slower, like what the previous presenter is talking about. So what's this slowdown means? So 1 second execution may take 10 days to 2 years, and this is only about single GPU. So borrowing a figure from the principal kernel analysis paper, like if the GPU time is a few milliseconds to microsecond, it may take a few hours to simulate. But if the execution time is a few seconds to a few hours, it may take weeks to centuries to simulate, right? So I highly agree with what our second speaker, Amir, was talking about. Like, we cannot really simulate at this level anymore. We have to reduce the workload for the simulator. So we have to simulate at a higher level of abstraction. So what is the higher level abstraction? We want to do operator level simulation rather than instruction or cycle level simulation. We want to collect the trace from a single GPU. Then we can simulate a multi-GPU execution. Right? So our users do not likely to have thousands of GPUs. They probably can collect just from one GPU, and then you can do research for 1,000 GPU, like OpenAI scale research. So that's why we created TrioSim. And TrioSim is a simulator for large-scale DNN workloads on multi-GPU systems. So let's talk about the design of TrioSim. Then at the basic level, we use the Go program language, which is a rare decision. But you have to trust me, it's really good. Why we use Go is we like Akita. Akita is the simulator framework that is developed by us, and is the simulator engine that is powering MGPU sim. So it already provides the simulation engine, data collection library, real-time monitoring, data visualization library support, so it can accelerate our development significantly. Then this figure demonstrates how TrioSim works, but I don't want you to understand in this figure. Let's break it down step by step. So initially we take an input. How we get an input? Our input is from PyTorch. Now we use a PyTorch profiler and a graph observer to build a tracer, and this tracer will generate these type of traces that tell us what CPU is running which layer and which kernel is running on which GPU, and also collect which tensor is being used by which kernel, which layer, so we get this data dependency. At the same time, we want the user to provide parallel execution schema, GPU configuration, and network configuration. Then in the front end of TrioSim, we build a multi-GPU trace extrapolator. So at the beginning, we only have a single GPU trace, right? The trace extrapolator can extend it into a multi-GPU traces according to the parallel schema and the network configuration. So we can change, say, training parallelism, network structure, or communication patterns. So at this stage, we support data parallel, tensor parallel, and pipeline parallel execution. Now for collective communication, by default, we support ring-based communication and the default NCCL or reduced algorithm, but we're also starting to support tree-based algorithms. So starting from this point, we have a multi-GPU trace. Now we can start to play these type of traces. How we can play these traces? Let's just focus on a single GPU part, right? So remember, we collect the memory dependency of each operator. So we first, the trace extrapolator insert many memory movement operations to guarantee the memory is on that GPU before we can start the operator operation, right? So let's talk about how we predict the time of the operator first. You can definitely use the time that collected from trace, but we're not satisfied with that. We use our previous work, Path Forward Beyond Simulators, which is presented in Micro 2023. In this work, we observed that the kernel execution time can be easily predicted using linear regression model, using a single floating point operations. So we use that model to predict our time, but this time is rather flexible. If you want to use Amelie or if you want to use GC scalar, then definitely you can replace this part with the other tools. So let's say if the operator part is rather easy to predict, then we need to predict the memory operation part. Then the memory operation part, the memory movement or the communication part. Then we build a rather simple network model that only uses bandwidth and the latency as the parameters. So just assume if you have 1 GB of data, then your bandwidth is 1 GB per second. It will take 1 second to move the data. But this is too simple. And so we add on to this simple model by adding link sharing, so congestion, routing, and end-to-end back pressure features to make it more realistic. Then by combining this compute model and the network model, we can predict the execution time, and other than the prediction time, we can predict the overall execution time, and we can generate timeline traces, or we can generate statistic information such as GPU utilization, network congestion levels. So this is TrioSim. Now with TrioSim designed, we want to run some experiment to validate TrioSim. So what's the accuracy level? We tested on 3 different platforms that include A40, A100, and H100 GPUs, and connected with different networks. And we tried many different type of workloads, starting from very small dense net to the very large Llama network. And we tried different parallel strategies. So let's look at the data parallel first. The figure is rather easy, but the most important information is we get very accurate result, and the error is only about 3%. And with tensor parallelism, our error is slightly higher, but it's still very reasonable. It's about 5 to 12% of error. At pipeline parallelism, the story is a little bit more complex. When we use pipeline parallelism, we need to break down the batches into smaller chunks. So when the chunks are large, or the mini batches are large, then our accuracy is pretty high. Then the error is like 5 to 10%. But just I want to highlight a few cases. This shows the limitation of TrioSim. Now, when TrioSim is not a good option for you is when these chunks are very high. Now, our batch size is fixed, is 128 images. Then when the batch size, when the mini batch is really small, then the overhead, the bottleneck is no longer the network and it's not the GPU. Now it's actually the CPU scheduling. In that case, we do not simulate the CPU part, and so we consider TrioSim is a simulator that mainly support like at least the network or the GPU is being stressed. Okay, so we have more validation report, and we have case studies in our paper. So if you want to know more detail, please refer to our paper. Now I want to talk about use cases of TrioSim, how it can be used. Then there are some moving parts. All of us use simulators, and we use simulators not because we want to just execute as is, right? We want to modify something to test our ideas. So there are some moving parts of TrioSim, then you can replace those moving parts. For example, we start with the parallelism, collective communication method, task scheduling method, memory management, network topology, and GPU devices. So if we change the parallelism, say what parallelism we want to use? Do we want to use data parallel or the tensor parallel? Or do we want to use some sort of hybrid parallelism? If we want to change the collective communication, what type of collective communication we want to use? Do we want to use ring-based, tree-based, or something even more fancy than this type of basic collective communication algorithm? And how we can do task scheduling. What if we have more than one user? How we can guarantee the service of quality support? Which GPU should execute which DNN layers? How the task should be, which task should be executed earlier? So those are all the research that you can do with TrioSim. Now for memory management, if you change this part, like you can answer a question like, how do you organize memory? Do you want to have a centralized memory pool, or do you want to distribute to other GPUs? Or shall we prefetch some data for future layers, or should we do rematerialization? For network topology, what are the optimal hardware topology for DNN? And definitely as how the product starts, how can optimal networks help on the scalability issue? For GPU devices, can we do like lower end devices, cheaper devices, easier to manufacture devices to do training workload, or we have to buy the real high-end GPUs? So those are all the questions that we can answer with TrioSim. At the same time, I have to say there are some limitations. Every model, every simulator has limitations, and you have to use it in the right way. So what is not TrioSim? TrioSim is not architecture level simulation, it's more like system level. So you cannot do something like if I design a page table working method or using zero copy like cache line level access, now what's the performance will be? This is not something that TrioSim is really good at. TrioSim must have the data on that GPU so that we can predict the execution time of that GPU. Now what about simulator? It's not a simulator for underutilized scenarios, so either the network or the GPU must be fully utilized. So if you look at the traces, the GPU execution time cannot have major gaps in between. Okay, so as a summary, so when we build TrioSim, we want to make a really lightweight, trace-based, and super fast simulation. Then we want it to be flexible. There are many moving parts that you can change these parts to support your research. And we want it to accurate, and it's actually very likely to be less than simulator level errors. Okay, then that summarizes my work, and I'm happy to take questions.